to flow of study over an airfoil. So firstly we go to aerotoolbox.com. We input all the parameters like the project plan, and then we show coordinates. We save this as a txt file to input it later in COMSOL, which will come later. Now we go to COMSOL 2D turbulent SST. After searching on some sources, we found that turbulent SST is the best interface. Now this will take a while. Steady, stationary. Now we'll change the unit to millimeters. Then we have to add the airfoil. So polygon. Now we'll input the same file which we saved as the txt. Build all the objects. This is the airfoil. Now we'll add a rectangle around it. And we'll input the dimensions which we have decided before. So it will be 1500 over here and 700 the height. So it should be in the center. 0 and x coordinate will be 250. So build. Okay, now we'll take the difference. So select this whole, subtract just the airfoil area. Build now. Now we'll input the boundary conditions. So here for the inlet, we define the inlet velocity to be 25. This is the inlet of the tank. And now for the outlet, this is the outlet side. And now we'll just see the wall. Yeah, this is it. Now we'll add the material, which is air. Browse material. Take a while. This one built-in air. Add the component. And you have done. Now from here my colleague Murtaza will continue.
Hello everyone, my name is Murtaza and now I will be presenting to you how we perform the mesh independence test. In this test we used lift force to find the perfect mesh size which we would be using in our project. We use different types of meshes, or from extremely fine all the way up to extremely coarse. For demonstration purposes we will be using extremely coarse mesh size, and now we build. As you can see, the mesh is built, and now we go to stationary where we start the simulation. This will take a little bit of time. Now, as you can see, the simulation is complete, and we can go to derived values, line integration. In this tab, we can see that we have used different expressions to find different parameters that we require. So over here, the first expression, the total stress in x-axis gives us the drag force, and the total stress in y-axis gives us the lift force. These are expressions which are there in COMSOL and can be used to find whatever parameter is required. So for us right now, we are interested in lift force, so we'll evaluate, and we get that the lift force is around 45.468 Newton per meter. So we take this value as well as the elements that were made using for the mesh. So and we use this and use all of these values to be put into this results table, where you can see we have done from extremely coarse up to extremely fine mesh sizes, and we chose the finer mesh size due to high computational times for the next to the extra fine and extremely fine. Moving on to the variation in lift and drag coefficient when the angle of attack is changed. So for demonstration, let me change this angle to minus 10 degrees. Over here, minus 10 is due to the clockwise rotation of the airfoil. So we choose minus 10, and now you can see the airfoil is rotated. We take the difference, and now the geometry is ready. Uh, we go back to the mesh size and we build the mesh, and the mesh is built, and finally we go to compute, where we start the simulation again to perform further calculations. Now the simulation is over. We go to line integration tab, where we'll be calculating the drag force, lift force, drag coefficient, and lift coefficient. The formula for drag coefficient is, as we know, the drag force divided by half rho v square into the chord length. So we can see half rho, this is the density of air, the speed that we have used, which is 25 meter per second, and the chord length of 0.5 meters. So if we now we'll use evaluate to find all these values. We get that the drag force is 8.8, lift force is 263 Newton per meter, drag coefficient is this much, and lift coefficient is this much. Similarly, we did this for angle of attacks from 0 to 20 degrees at an increment of 2.5, and we tabulated these values into this table, and we found that the graph is like this: drag coefficient versus angle of attack graph. You can see it is increasing as angle of attack increases, as well as the lift coefficient versus angle of attack graph, which you can see over here. Furthermore, we also did another study where we tried to find how the wake region size increases as the angle of attack increases. uh, I'll not show the simulation again because it takes a lot of time for larger angle of attacks. But as you can see over here, this is the streamline for an angle of attack of 10 degrees. Same thing we did for 20 degrees and 30 degrees, and these are the results that we got. As you can see, angle of attack of 10, you can see the wake region is not that much, but as we increase the angle with 20 degrees and 30 degrees, the wake region increases. And now my colleague Abdeli will be continuing with the presentation. Thank you.
We will take a look at how we can plot surface velocity magnitude plots, streamline plots, and pressure contours in COMSOL. So to plot the surface velocity magnitude graphs, we first open COMSOL and we go to the components tab and make sure that our airfoil is at 0 degrees. We open geometry tab and we check the rotation. So we can see the rotation right now is 0 degrees, which means our airfoil is completely straight. So we'll get velocity magnitude when our airfoil is at 0 degrees. So then we make sure we have done our mesh. We are using finer mesh for the study, and then we open the study tab and we click on step to stationery and we press compute. Due to us using finer mesh for this problem, it takes a bit of time for the problem to solve. So we'll just fast forward through the whole solving process. Okay, as we can see, a solution has converged and it has already taken us to the velocity magnitude plot. And if we don't see this plot directly, we can just open the results tab and we can click on the velocity profile tab. Okay, so to create a streamline plot, we just click on the velocity tab. Then we click on duplicate. So we just create a duplicate of the velocity tab. Then we open the tab and we just add a streamline to this plot. So then we click on replace expression tab and we type in velocity field over here. So it shows the velocity field, and then we select the inlet from where the liquid is entering. So we press on this boundary because we want the air to flow from this boundary, and we select the number of streamlines that we want to plot. So we can change it from 30, we can change it to 30, and then we can also select the color of the line. For example, we can just choose a red line for demonstration purposes and we can press on plot to plot the streamlines. Now sometimes the streamlines aren't visible because of the surface velocity magnitude plot behind it, so we can just disable the magnitude plot and then we can plot the streamlines, and then we can see the streamlines clearly. And for the pressure contours, just like the velocity magnitude, we can just press on the pressure and it will automatically show us the pressure contours. So this is how we plot surface velocity magnitude, streamlines and pressure contours.